electron transport based on the band theory. We said that the mean velocity of electrons can be expressed as the gradient of the energy. This is one of our few conclusions from the last lecture. Now I would use a few minutes to go more in depth on this, just to discuss. It's nothing, no new material, don't worry. And then we continue with the transport and searching for our current. So, I think I mentioned last time, if you have a free electron, you just have parabola, no? Which continues, no? Even beyond age boundaries, if you would have in a free electron case. Fine. Its velocity keeps growing. Yes. Velocity in this case proportional to, well, it's equal to hk over m. So velocity keeps growing. This was energy versus k. This is velocity versus k. It keeps growing. Now, in our case, we can look at quasi-free. I'm always going back to the same things. If you notice, there are just a few things I keep repeating in one way or the other way. In the quasi-free, or nearly free, you have at the edge boundaries, derivative 0, gap opening, and the energy continues. So you have actually just a small perturbation at the edge boundaries, no? You remember this. But the velocity changes greatly. If you look at the velocity, it's going, oops, a bit too far, negative, and then positive for this case. So again, energy and velocity. So you see how putting this electron in a lattice is completely changing not only its dispersion, which is barely changed if you look at it, but its velocity. And now I will take a few minutes to discuss this. I'm warning you beforehand because in previous years they were people a bit confused. What we are doing here is velocity as a function of k. We'll derive on the blackboard this proof of Bloch oscillation. We'll derive how it does. You've done the homework? Yes, all of you. But also as a homework, or who wants, I'm not sure I have time to do it on the blackboard, you can also derive velocity as a function of x in a real space, just to help you. Because I noticed previous years people were getting confused. So this is in the k space, how velocity oscillates in the Brillouin zone. Okay, just to make this a bit more clear, I will start again from a electron case. I can use this picture. So, for the quasi-free electron, I will put names. I forgot how I called them. I think here are A, B, and then C and D. These are the points of inflection, D and A. I will write my wave function as the phase in 1D times okay, first. But if it's in 1D, then there is no need. Here the G is a reciprocal lattice vector. We are at pi over A and minus pi over A. And we put this in the field. Now put the thing in the field. I'll put electric field in this direction. So what will happen? Electrons, the states will start jumping. You remember we derived this dk over dt.
Yes.
So it's a constant rate how it's changing. And going from 0, let's start from 0. Going from 0 to A in a quasi-free picture, we have completely free electron kind of motion. Completely. Parabola. Velocity will be even linear up to a point. And we will have here an expression and B will be, now I put the G vector, from A to B. No, actually from 0 to A, this beta is 0. This is important to say. You have a free electron kind of thing, no? From A to B, you start feeling the effect of the periodic lattice, of the Bragg plane, which gives you crystal momentum in the opposite direction. It kind of pushes, like gives a force in the opposite direction, which is this part. And this is, it makes, here it stops at some point, and it starts decreasing its velocity. Okay. At the B point, at the very edge, what will happen? K is pi over A. And my psi, my wave function, will be equal I pi over AX. Beta is maximum. So this is equal EI pi over X plus E minus I pi over AX. Okay? Now I didn't put any factors, any amplitudes, normalizations. At B. So from 0 to A, beta and alpha are 0. Beta starts growing. At B, you get this. What is this?
Cos pi minus.
Fine. What kind of wave is this?
It's a cosine. It's a cosine.
If you have a wave, I mean a situation where you have an incident wave and the wave in the opposite direction, stationary standing wave. Or stationary. So it's time independent. So due to this lattice, you will get to a state of an infinite wave, standing wave, due to lattice, no? Now imagine, remember Drude, what we said, that he was approximating lattice by the interactions of electrons, collisions of electrons and ions, making a collision and bouncing and going further. I mean, how approximative that was. The real effect of the lattice is this, that you create a wave, infinite wave, time independent, just due to this presence of the lattice, essentially. Okay? At the C point is the same. Just here, you will have free electron moving this way, and the crystal would give the momentum in the other direction. So it will just be all, you will have alpha component largest here, and then diminishing to the free electron case here. Okay? So here we see that at this state, due to electric field, really oscillates in the Drude zone. And it's something quite just purely from the theory. I'm not here talking about the reality because of the scattering, which we mentioned. But this is the single effect of the lattice. Okay, I will erase. If you have any questions, now it's a good moment. Also, last time, we were trying to derive current.
Excuse me.
Yes,
The Just look up that first formula and explain it again. Right?
Which part?
How it comes about. The first formula.
This one?
Yes, yes, yes.
Oh, I just wrote it. It's the free electron. I wrote in a block form. This is the phase part,
Okay.
and the periodic part. I use the G vector, which has the period of the lattice. The simplest way to write, because I was trying in one equation to write for all situations. As you put the field, how it will change the states. Otherwise, you can just use for a single case. You can just use one part.
Yeah, but I thought that then we wouldn't have delta and then beta.
Because they are growing. They are growing.
At
In the
different
beginning,
rates.
alpha and beta 0, because you have purely a free electron, plane wave.
So we have cases where they are growing at different rates.
Or maybe I wasn't so clear in the end. The idea was to show as you put the field, electric field,
Yes.
what happens. So you go from the free electron-like case to something which feels more and more the influence of the lattice. And that influence of the lattice can be expressed by the growing alpha and beta, or beta, depending on the side you go. That was the idea. And just interrupt. If I'm going too fast, if I skip something, interrupt. I'm talking everything in terms of the E field, electric field. But what I have if I have magnetic field? Huh? You can still get these things, no? The force will be VXB, vector product.
Yeah.
So you can still get, I'm just making it simple. All this is a semi-classical picture. Extremely simple, not to confuse you. So last time, we started from equilibrium case. This is still a review. Equilibrium case. We we said that if you have equilibrium case, some occupied states, then your current will be proportional to the sum of the charge and the velocities. But we know that velocity is antisymmetric. Around in this case, velocity would have the form, okay, I can draw again, velocity is like this. So as long as you have equilibrium situation, you will have equally many contributions with positive and negative velocity, your current is zero. Okay. Then we even put the field. No? The second case, this was the simplest case, then E larger than 0. We showed how it will propagate under the influence of the field. Actually, you will get them to move a little bit. I will talk more about it today. But then we looked for the time average, or the space average current. It was easier to express it by an integral over the full brilliant zone. Here it lacks a factor. Maybe I put equal last time. It's not equal. I'm lacking a factor here. And the velocity, the charge. So this was the gradient of energy, and was giving us again 0. Okay, this is very soft. And we said we need scattering. This was our conclusion. So we need some real situation. And the scattering can be due to impurities, due to electron-electron interactions, or even interactions with phonons, which we'll mention, which we'll learn soon what it is. So, scattering is the missing thing. impurities, electron-electron, electron phonons. Fine. So let's include scattering. The first situation today, continuing on this previous, will be completely filled band. Okay? Now all the states are filled. So what does scattering mean? Scattering means that due to these interactions with these elements, due to those, you will get states go into usually lower energy states. It will find somewhere a low energy state that it can go. However, in this band, it's all occupied. So under the effect of the field, the only way you can get them move is to move them collectively in phase. Because for this guy to jump anywhere, the next one has to be free.
Yes.
So they all have to move in phase. This one will go here, this one will go here, simultaneously in phase. And what we notice, the picture in time doesn't change. I can express current through this or through this. It will be zero. Do you all see that?
Yes.
Okay. Now I ask you, what does this mean? Take a second. What does this mean if we get that the current of a completely filled band is zero?
That means
Okay, please give a chance people to talk. I want everyone to reach this, sorry. You have an idea also? Everyone? What is the meaning that the current of a completely filled band is zero? Any ideas?
I think
I mean, you're free to talk.
Yeah.
You're still sleepy, I guess. I am too, I mean, if it helps.
okay. For me, I think that if they say the current of a completely filled band is zero, then because you talked about shifting them completely, so I think as you shift an electron to fill another space, the same another electron is going to fill the
Yes,
this
I mean,
whole
that shows why. Why it is zero. What you're saying is correct, it shows why. Now I'm saying what is the consequence? To what we can connect this, what we learned before. Maybe I wasn't asking the question clearly. Completely filled band, insulator. That's what you wanted to say.
no, actually.
Okay, tell me. Sorry for
I was
interrupting.
just, going for the call. I was just saying that there is no possibility of lowering the energy anymore.
Yes, okay. This is all going into why. Why we get this current zero. You all understood why zero. Now I was just trying to see the consequences of it. What's the meaning of it? And actually now we are connecting. You know that, I mean, insulators do not conduct. And this is why. So there you have a valence state, which is completely filled. And if you have a completely filled band, even under the influence of electric field, or magnetic, but electric field is good here, even under the influence of scattering, even if you have scatterers present in any density, any number, you cannot make current because the full band is occupied. You can look at the time average, at the space average. You can just say I have equally many positive and negative velocities, which will sum to zero in the end.
Excuse me.
Yes.
No. My question is, okay, I don't know how may seem stupid, but
No, stupid.
if you have a finite crystal, and then I'm wondering, yes, you are shifting the electrons completely, okay, well, connect collectively in phase. What happens at the boundary of this side?
But you always have a gate or something. But for
Have what?
you always have some gate. You have to put voltage. You have to collect them somewhere, no?
Mhm,
You have a
yes,
copper
yes.
line. It's to something connected, no?
Okay.
Okay.
And
For
what
your
happens?
case, there is a flow. No? I mean, the absolute thing is moving, but it's not the question here, the relevant question. You're also confusing what you have, the real space and the real zone. So try to derive the v of x, the velocity as a function of x.
Okay.
And anyway, for what we are doing here, it's a bulk. We always
It's a
assume
bulk. Okay.
infinite case. You have to have n very, very large to be able to apply Born von Kahneman and to derive these things, because you don't take anything finite into account. But we can know from practice what happens. No?
I mean, that would be very difficult in practice.
Sorry?
It would be very difficult in practice.
Okay, now we are coming to practice. What we can say about Bloch oscillations in practice. So here we see an insulator won't have current. Should I start here with the homework or the next step? I'll ask one of you to come to solve it in 2 minutes, but okay. Let's see what happens if you have a partially filled band, electric field, and the scattering present. Now we are going full force. We cannot invent anything more. Why do you always start with occupying these states? It's clear to everyone. I always start with the lowest energy states.
Yes, yes, yes.
Right, and I put the field. And imagine first no scattering. Huh? To start first no scattering, what would happen? This would change by delta k, and this guy here, they would all shift by 1 delta k. And then for one more, and one more. And this part, the segment, will be moving. So in some later time, let's say t is 0. Some later time. And even later. It is just shifting as a segment.
Yes.
It's going around. Now, this case, electric field, partially filled band. In this case, will I have any current? I have no scattering yet. I have this segment moving. In one period, I will get this point to move to this position. So this point here, one state starting from here, I mean one state, it will change the state,
Yeah.
will go through all the states. So it will have equally many positive and negative velocities. It's the same reasoning as before. If I take time average. Do you agree? Do you all see it?
No.
The time average of one period will be again 0. Because this state, what was initially this state, it will move through all the states during one period.
Yes.
I take the mean velocity of one period. And again, it will be 0. The same argument applies. I'm taking the average. It's fine. Good.
Excuse me.
And now I'll take the scattering. Yes, John.
So if it is not the mean velocity, it will not be 0.
The phase velocity. But this is the velocity of all things. Yeah. If you take electron as a wave packet, you will just look how the whole thing moves, the wave packet. You don't care about the phase velocity. Okay. Now, plus scattering. The scattering will will usually shift the state to a lower energy state. So, in a situation like this, let's say, I will find a state somewhere here to shift a lower energy state, to shift it down. This is the effect of the scattering.
Excuse me.
Yes,
It starts from t equals to 0.
yes. And here it's symmetric, let's say.
Yeah.
No field yet.
So if
And-
we include scattering and field, why would it bother to change? Because that is the lowest we can have.
No, the
Symmetrical.
field will go like this. No, from here there is nothing. Because all energy states are occupied, lowest energy states. It would have to scatter into something high energy. It also can happen. Huh? But mostly.
So is it something like the war between electric field and scattering?
Exactly. No,
This-
this is plus scattering. Okay.
So because electric field will always try to like push it.
Makes it change
push it-
delta K, dk over dt. This is, I mean, the consequence of this is that you have a constant rate of change of K.
So if it's in this way,
you're
electrons
sweeping
will
over
always
all the states.
move here. But then scattering won't allow that because
Echo.
that is
This-
it can't go because scattering will pull it back to
Exactly, exactly. This is where we are arriving. The scattering will pull it to a lower energy state. So if we have something here, it's going down. And the scattering, time scale, it's very fast. It's around 10 to the minus 14, I hope I do it well. It's extremely fast. So it happens immediately. Okay. I would leave this here. I would ask one of you to come and just derive this R of t, how it changes for a 1D, because that's related. Quickly, in 2 minutes.
I think I can start, but I think like there is some problem with going to the x space and k space, but I think I can do it.
Some of you who didn't have I mean, just a quick thing. I don't like to take you always. You done it? Can I see?
No, I didn't do it, but I have the energy and then you go to
I want to go quickly. Some of you have done it? You've done it? Just to make it quickly. Okay, yes.
This is what I have.
Are you okay?
I first derive the energy
This
and
one
then go to the
day.
velocity. And then, like, maybe here one is I'm not sure, but I put in K, which is order to make velocity a function of time. And then I got RT by interpreting.
Okay, this is good. Come, quickly. Quickly, because this is like, now I'm opening parentheses. We will stop here, I'm not deleting this. We will continue here. Just, I want to remind that indeed you get these oscillations. And then I'll go back to what we've done so far and talk about observing these oscillations, because they should be there. Just quickly. So what is the dispersion?
The dispersion, it is,
In 1D, we won't derive it, we'll just write.
it was just twice.
Yes. And just
So
write
I
the
just write it?
solution. Yeah. On cosine. Just do the cosine. Okay. So this is a 1D tie binding. You all got it down. This is nothing. And then we go. Velocity, we know how to get from the. Okay, we are in 1D, so it's fine not to write vectors. Good.
Yes. I came up with first gamma over h cut, then times a.
Please
and
check them in for the coefficients and the.
sin. I think that's it.
Okay.
Yeah. But then there is a formula that we derived for kt, because as a function of time,
Yes.
I got negative over h cut plus k naught. So I just plug it in here. You get vk, okay, as a function of time, which is twice gamma over h cut a, then sine of negative t over h cut plus k naught times a. And then we know that velocity is always the r dt. So if I have velocity as a function of time, I just integrate it to get the position. And r is integral of t dt. And I came up with
You have to change, this is a new variable, and okay,
Yes,
I mean
yes,
for
yes.
the integral, but you can just put the solution and then you can will check if it's correct, the coefficients. You get the same coefficients?
Just without
Okay,
the
plus
A.
a constant.
Without the A?
Without the A.
Where here?
Yeah.
Oh.
Yeah, I also think it should be there. Because you have to take it as a coefficient, yeah. I mean, you take a new variable for integration, you call all this a u, and then you have to,
Okay, it's an integral. Yes.
yeah, good.
Yes.
So, good, thank you.
Yes.
What was the problem here?
No,
That V is the dr
no,
over
no,
dt?
no, no. I got the same result.
Yeah. Sorry, I want to be fast here. This is, when it is closed, I'm closing parentheses here. We indeed get what we expected, that the coordinate position of this state actually is changing time periodically, just going through the whole Brillouin zone, as what we said, under the influence of the field. This is all under the field, no? So, one should be able to see it. I already anticipated that they tried. These Bloch oscillations were predicted, I think, in 1930s. And the first thing, experimentalists went to the lab and tried to see it. And no, they couldn't see it. I think I already said why it was difficult to see them. Do you remember?
The time it takes for that to happen, and the time of measuring it, if it's different.
It's related, it's close. But the problem is of the real world. Bloch oscillations, in their derivation, there was no mention of scattering. No mention of scattering. And okay, let me say that the time to sweep Brillouin zone, how was it? plus h dk over dt is EE. I never remember this thing, sorry. I have to h 2 pi over a lambda is EE. No, not lambda, t lambda, and then tau lambda, and then this you have in the notes. I just don't remember how it is. h2 pi over a. Okay, and this tau lambda, the period to sweep over the full Brillouin zone, is of the order of 10 or minus 10 seconds. So it's quite a bit larger. And this will scatter. This will make always go down. It will prevent it from making the full circle that they could observe in experiment. So, very hard-working experimentalists try to increase this time. They made samples cleaner and cleaner and cleaner. But what can you do about electron-electron interaction? You will remove impurities. You will maybe reduce this 10 times, maybe 100 times, but you still cannot reach this point. It will scatter, maybe a bit later, maybe it will reach this point before it scatters, but it will eventually scatter. It won't make the full circle. So now talk with your partner and think of an idea how you could measure it actually. Because this you cannot reduce to this point. It will always. Tau lambda is, oops. I'm getting better, not just one a class. How can you do it then? Think, discuss. Or close your eyes if you prefer.
By sweeping the electric field.
No, this is all under the field. We are constantly putting field. Without field, nothing. This we know. I mean, without field.
I think that is the variation of electric field will change the.
No, but Bloch oscillations are under the field. If you don't have the field, you won't have electrons be sweeping around the Brillouin zone.
Magnitude of that electric field.
You want to increase the field. Then you will increase dk over dt. But then, putting the field even stronger, you change the bands. You have influence which you are losing the symmetry anymore. You can get the band skewed and okay, that's not ideal. Talk, guys. You're really not interested in talking. This is too fast.
What about freezing the time? Measuring.
I cannot hear.
Go down to lower level.
Yeah, it would reduce scattering,
Yeah.
but not at all the
Also,
time.
think.
Yeah, but yes, it will help. I mean, it will help because high temperature makes it scatter more. So, I was TAing in the States, and the guy who was teaching, Emilio Mendes, he was the one who measured this in 90s. One of the first few people. At the time I didn't quite, I wasn't so impressed. A bit later I realized how hard it is. You're really sleepy today, I see that. Fine, I cannot make this longer. What about this? Can I change this number?
If you change the
Now, I'm not saying I had to observe this Bloch oscillation in the same aluminum, whatever I had. I just want to observe them in a material, a crystal, anything.
That means we have a window through A, small a. Because
Yes.
E we can't, other things are,
Yes.
there is no way out, so.
So I have to create somehow some structure which will have this A 10,000 times larger. Periodic. Huh?
Excuse me now. Like, everything we are doing in K-space right now.
Yes, yes.
What about that position? That was the real position or the position?
The real. This one is oscillating in X.
Yeah.
because we transform k into the units of time. But at home, really, you derive this velocity as a function of x. That helps, I think. It's not an easy formula. You'll get some cost
Yeah,
and
because
our cosine.
we change into time, and time is time in both the k and x.
Yeah.
So
But I mean, really, it's a good exercise, this one. I
because
think.
if we had derived like velocity as a function of x, it would be much more clear. Like we don't have
Yes,
to go through.
try,
all
but
that.
it's a bit ugly, so you might have to use some tables. I mean, not ugly, it's, I mean, you might not know it offhand, like you have to check something maybe. But it's a good exercise. Okay, so I want to reduce this number some 10,000 times, and they came up with, in 90s, 92, 93, I think. What is ringing? To create a semiconductor superlattice, which has many layers of one material, many layers. And then a different material, still layers. So this became, and then again the first material, like A, B, A, and now this became a new lattice constant. A layered structure of many, a new A, which is roughly, let's say, 1,000 times old A, which was here. And by this, they actually reduce this tau lambda, the time you need to sweep the brilliance zone, because this is larger. 2 pi over A prime is 1,000 times smaller. So you make a very small brilliance zone. Before this scattering can take place, you trick it. And we observed they actually plot many things. You can see as a function of electric field how it's changing. So this is experimental observation of Bloch oscillations.
Excuse me.
Yes, yes.
How was that E increased? Like because E is
It's a trick.
connected-
No, this is a new superlattice. This is the A of a superlattice, semiconductor superlattice.
But E is a very primitive thing in the sense that a volume created by A, let's say in a simple cubic, A cube would contain one lattice point. So that should be preserved. Is that
I mean,
preserved
you
in
always
this-
have a superlattice. I mean, you can create. Now, this is more complicated. You know that we did the lattice with a base, so it can have 2 atoms in a base, 10 atoms in a base.
But the number
Here, the
of
base
lattice-
is huge. If you want to take it that way. The whole thing, you want to have a periodic structure. And you have it, just it's very complicated. When you have hundreds of layers, and they have maybe some BCC structure or something inside, then you have, in the same lattice is the best, hundreds of layers of some other material, and they together form, and then you repeat with the first one, and they together form a periodic structure for which you can create a
it's just
new A.
like, we can have a simple crystal with 1 atom, and then if we replace that with, let's say, 10 atom basis thing, the primitive
Well,
this
it
will
depends
change.
in what
Like it has
structure.
to increase because it has to like have all these 10 atoms inside, something like that.
Yeah.
You said like increase in basis.
Yeah,
basis
it's one way to look at it, but for me it's easier to just look as the periodic structure you want. And then it will be this periodic structure which will be the main thing for the derivation of the crystal potential, and just much more complicated. But indeed, it was reacting with this A, with this tau. So it's a trick. You have to do many tricks in physics to get to measure something. Where am I? Okay. Here. So, any questions on this? Any more questions? Let's just summarize this. We express the current as electric charge times velocity, or I can do it as an integral, maybe better. I think it has a phase factor charge and K, dk, for example. I mean, one can go to either way. In our semi-classical picture, I'm asking you, how will this current qualitatively depend on the scattering time? If I increase the scattering time, is the current decreasing or reducing? Feel free to discuss, to talk. So, if I increase tau scattering, if I make it slower essentially, if I increase it, making it slower, now you understand. How, if this becomes 10 to minus 10, so I'm increasing it, making it slower, you understand? It will allow this thing.
Current will decrease. Decrease. Because if we, let's say we increase it so that it's too large, that means there is no scattering. It's something like there is no scattering. So in the theory with no scattering, there is no current.
No, this is the opposite. It's just the opposite. If you want to observe Bloch oscillations, it's the way. No? And Bloch oscillations is the opposite thing of the current. Now, maybe I didn't make enough contrast. One side is Bloch oscillations, when you get the states oscillate, and it's just the opposite limit of having the current in the crystal. Because if it keeps oscillating, there is no current. Okay. And the longer this thing is, the larger it is, the easier it is to observe Bloch oscillation. So it's just the opposite limit we are looking. We are looking for the current.
So, but you said if you increase it,
yes.
If you increase the scattering time, then current will go down. Current will decrease.
No.
That's what current increases.
Increases. Increases. Because you will be able to shift, to make it more symmetric. If it's very fast, it will start scattering already, like at the first asymmetry, it will start scattering.
Yeah.
And will be almost symmetric, this distribution of occupied states. The longer you allow, you will reach more symmetric position, and then all the states, if you have like this condition, that only these are occupied, and nothing here, you have stronger current.
But then, ma'am, if we increase it to a very large value, let's say for some time,
Okay.
1 second, let's say.
Ooh.
No, let's say.
Okay.
But by that time, there will be.
Okay, it's too slow.
Yeah.
No, you
In
cannot
that
talk
window,
beyond this. You cannot talk beyond this. This is
Okay,
the
we
limit.
can decrease it, increase it beyond that. Okay.
Doesn't make
Because
sense.
I was thinking like
Doesn't make
if
sense.
we could increase it
No.
like larger than T lambda, then
Doesn't make sense.
it's just like no scattering case. So
I
was
agree,
going
no,
that
but
way.
this is the limit.
Okay.
Okay, so we agree that the current is proportional to tau scattering. I'm not putting any dependence now, I'm not denying it. And if I put stronger field, will the current be stronger or larger or weaker? Electric field?
Larger, smaller.
It will be stronger.
I think it's quite obvious. You will have more driving force to move. So this is the dependence qualitatively. Just to be able to think of
Excuse me,
it.
does the
Yes.
scattering also depend on the field applying?
Oof. It might, but let's not go into that. I mean, it's not. The idea is it's independent, but in reality it will depend. Especially if you have, for example, charged impurities. They'll be moving in the crystal as well. But okay, it's a different. We are doing very, very basic things here. Okay. Any questions? So here I will run the current over the full brilliance zone. The full brilliance zone. As the current over, I'll just divide it in two parts. I will say these states and then the rest. So the first part, I call it field, but it's always the same states, field states. I mean, there is this factor of 4 pi cubed everywhere, the phase factors. And then the remaining states. No, just these states, remaining ones. So I'll call them here field and empty. Although at this point, it's hard to understand what I'm calling field and empty. I'm just dividing in two groups of states, the low energy states and high energy states. So this is a bit artificial at the moment. Okay. So if I have full brilliance zone occupied, I know that the current is 0. And then I can write that this over field states the current is equal minus, and minus gives plus, empty, so I get two currents with the same sign but different charge. One has minus electron, one has plus electron charge. And their currents. This is actually related to, until now we were doing mostly metals, no? Now we are going into something slightly different. Yes,
I'm now confused
Okay.
because you said that the empty states, we take them as poles, right?
Okay, no, I didn't see it, but yes. I just said divide the brilliant zone,
Yes,
the occupied states, I mean the what they call here field states,
yes.
the lowest energy states, and then the highest energy states. Imagine it's all field.
Yes.
So I have the current coming from these states and current from the higher line states. I said it's not yet clear why I call it empty. It wasn't clear yet, I mean. But now express that the current of these is the same as the current of these with the opposite signs. This is what we just derived here. It's a simple thing. We said the full Brilliant zone field, completely everything. I can artificially break it into these states. Imagine these are the same states. Huh? So I can actually choose to calculate the current. And if you have, okay, this was the fully filled band. But if I have a case of partially filled band, I can choose to calculate the current of that one, either by summing over all the electron states here occupied, or by finding the current of the whole states, the missing states, which have positive charge. So this is a very useful trick, that if you have a nearly filled band, shape. It will be something of this shape in the semiconductors. The Fermi energy will be here. You know, at t equals 0, it's not clear where to put Fermi level. At t higher than, you remember this from the Fermi Dirac it comes, no? That you have to have equal number of states taken from here to be given up
Yes, to be
there.
exactly in the middle.
Exactly in the middle of the gap. No? You remember this thing? Everyone?
No.
Who is saying no? You? Okay. This is the Fermi Dirac. This is the gap. E gap. And this will be equal to 1 over A E gap. This is 1/2 2kT plus 1. So, as many states as I take from the occupied, I will put in the empty. That's why it has to be symmetric. And the Fermi level, which is the center here, has to be in the middle. Okay, so I will unhave. Huh? Is it fine? This is like I'm reviewing from
Yes,
the.
yes, I understand.
Ah.
However, this equation, why is it that the mathematics does not leave 0
Mathematics, sorry, what mathematics now?
on that equation of the integrals?
It gives 0.
But
Here.
it's negative E, and of the same integrals.
I'm confused.
The limits are different.
The sum gives 0. The sum is the full state in the gradient zone. Occupied, the band. Let's go from one band. One band.
The boundary is
Yes.
Yes, yes, yes.
And then I'm going to apply this. Where I had states here and states there. I'm going to apply this to a semiconductor. Let me say. Now I'm going to partially, well, not even partially fill. Let me just call semiconductor. At t larger than 0. Let me remember if I know. At room temperature. No, I don't know. Maybe I have it written here. At room temperature. Okay, good. I have the numbers. So, at room temperature, RT, if I have a gap of the gap 0.5 eV, number of carriers is 10 to the minus 9. If I have a gap of it's not clearly written, sorry. Yeah, okay. 1 eV, it will be 10 to the minus 18. 2 eV, 10 to the minus 34. What are these numbers? This is the number of how many electrons I will actually transfer to the conduction band from the valence. So, this is field up to the very top. Just a few states on the top are not. I mean, look at these numbers. These are tiny numbers. Tiny numbers. But they can be observed. So we have almost field band. Almost field band. And in this case, it's very beneficial to use this. That actually I can sum just by those 2-3 states and find the current of the whole instead of the whole thing.
Excuse me.
Yes.
But is it necessary to bring the idea of semiconductor right now? Because
it is where this is the applicable. Empty states.
But ma'am,
Yes.
if the
Ma'am,
first
Natasha?
first band is not filled completely, it is metal. Why do we have to go to the next band? Because even if it is not completely filled,
I'm not following.
if the first band is not completely filled, then it is a metal.
Yeah, but I can have half-half. And then the application of this thing is not so obvious. If we have half filled states, half empty, yeah. I mean, you don't get why you would go for empty states. But the obvious application of this is when you have really just a few states, a tiny portion of states which are empty here. And this is a semiconductor.
But then,
For metal it can be, doesn't have to be.
We also have to introduce temperature because
Fine, I put it. I mean, otherwise you won't
because
have.
without temperature, it won't jump to the higher
Sure,
state.
you won't have here anything empty. Yes, I agree. But what I want to emphasize is you can either calculate the current of electrons here, those few, or the current of holes here. It'll be the same thing. Because it's the same number of carriers. It's true just around the gamma though. Yeah. Let me see what I would like to say more here. Yeah, okay, that's covered. Any more questions on this? Have you heard before the concept of holes? You've heard it before.
For sure.
Okay.
Not so much. But I've had it very much.
Okay, I mean, it's not something complicated. I mean, the empty states here are called holes
Yes,
and carry positive charge. I mean, I had people asking what is the hole after you finish the lecture, so better that we discuss it
The
earlier.
concept of positive is also ambiguous.
Well, it's just the lack of negative. Because positive. Fine. Okay, then we'll move to the, yes.
So this idea we are using this just because it will be easier to sum over the smaller number
Yes.
of empty states. That's why.
Yes,
That's
yes.
all. Otherwise, if the temperature was 0 and we had half filled state, then there is no point in using this because it's the same thing. Okay.
Yeah, I mean, it's, you can do it, but you don't gain anything. Time is really flying. You have a class after this?
Yes.
Okay. Should speed up a bit. Okay, so coming back to our force which we introduced last time, it was, we said, now here also can be the VXB, but we're not writing it, but in principle you can do it. We can actually introduce, just based on dimensional analysis, some scattering force. It has the right dimensions, and this is what you know exists there, and you describe it as some mean value, because there are different types of scatterings, different effects, which all have different hours, but different processes, no? But I will just put it as a mean value, just to say it exists there, to remind me. And if we leave it here, will come useful, and it will go to derive a very important concept. One more consequence of the band theory. So, starting from velocity. I can write K alpha component. Now I'm looking for the alpha component of this vector.
Yes.
Okay, let me just write carefully. K alpha. Okay. And I will express the derivative of velocity in time. Component. Oops, this is component, no vector. Yeah, sorry. Just correct me. I like. I tend to make mistakes. Okay. I'm writing it in a very complicated way, but it's actually something very simple. K data. So all these three, Vk alpha, and then putting, so I make derivative over k and add dk over dt. I think I'll use something similar. Is this okay? It sounds complicated, but actually it's really not. Here I express an alpha component of velocity, and here I find the time derivative of that. But for me, it's easier to find the time derivative of k, dk over dt. Fine. And now this further is equal. This I know, no? Is equal to 1 over h sum over beta I have only alpha component because I have only Vk alpha of energy, and they still have dkb over dt. Fine. And now I will add one h bar here and here, just to make it easier to see. I want to write in the same way. So this is one derivative and second derivative of energy. You agree?
It's fine.
Excuse me, ma'am.
Who is in charge?
Why the derivative is not acting on the decay beta on the t?
No, it's not. I'm adding this part here. This is like, because I didn't know how to take time derivative of velocity. So I said, let me take the derivative in k, which I know how to take, and then add this term. I could write this in front. This is what? I wrote there. It is a component of force. No? And what is this?
Position.
No, this is
Acceleration.
dv. This is v, velocity. This is
Oh,
the
sorry,
change,
acceleration.
acceleration.
Yeah.
We have acceleration, we have force, and something else. This looks like
Newton's.
Newton.
Newton's second.
So I can indeed write, let me see how I called it, not to make it dv. Use the same, I don't want to change from here to here. dvk over dt. Now this was in components. Now let me write this. So this guy here has to be dimension of 1 over s. 1 over mass. Inverse, no? Because you have acceleration and force. Force equal ma is Newton law. So this I'm calling a tensor. Inverse tensor. because you can apply force in one direction and look in all directions how it changes the acceleration. This guy here, it's called effective mass tensor. And can be expressed as the inverse of the second derivative of the energy dispersion in K. So the first derivative of energy in K will bring us to velocity. The second and inverse of that says what is the effective mass. What is the meaning of effective mass? Under the influence of electric field, electron will move in the crystal as if it had this effective mass, not its rest mass, which we all know. How much is that? 10 to the minus 31 kilograms. Not like that one. It will move to the crystal as if having this effective mass. So if you have a free electron, let's always go from the simplest, we go for limits, not for the simplest things. The effective mass of the free electron is equal to what? Second derivative brings you 2k h squared, and then k brings you 1 over m and times h squared. And this is just, you take the inverse and you get m. So for the free electron you get m. Limit is working, that's fine. Yes?
If we go to, let's say, 2 or 3 dimensions, would
Yes.
it also be m? Because there are...
Yes, I mean, if you just have free electron without any crystal
I
field,
think, yeah.
it will be. But without crystal field. As soon as you put periodic lattice, be it a simple or a complicated one, you will have a dispersion which is at least altered at the edges. The minimum change is you have a quasi-free or nearly free, but at the edges it becomes smoother and opens small gaps. And at those edges, what will be the velocity? dE over dk will be 0. But this is inverse. Think of it. Next time we will talk about it. I want you to think before I discuss and give you the... How can it be? What's the meaning of that?
Yes.
What is the meaning of that?
Infinite mass.
Infinite mass. Just think of it. I mean, I'm not putting... I think I should give you a problem with that. But it's a good thing that you go through it. And then I think I wanted to apply this to the free electrons. Yeah, nearing the end. So, let's continue with the free electron leg. What we already started. We go from here. And I'm writing that velocity in this case of electron leg is equal h k over m, and effective mass is called both mu, m star. It has a few symbols. I'll be using both of them, all of them. I mean, it's not that I use just one symbol. And then go to this expression. So I can write that m star d vk over dt is equal I just plug this into this. This is my what I derived just on the basis of the dimensional analysis. I put the force by hand inside, just to describe the mean effect. Is it okay? I just plug it in, combining, relating k and velocity.
That's M star or M?
M star. M star. Sorry. And now I'll choose a stationary condition. And dv of k over dt is 0. I don't have acceleration. And I go back to the case of a semiconductor, where this concept is used heavily. And I can express the energy, E of k is equal to E0 minus h squared k squared over 2m, and here are holes. So this is the hole effective mass, and here are electrons. So, when I'm imagining semiconductor, this is kind of a typical graph I have in mind. Can you all see? So I should write higher. And the Fermi energy is in the middle. So here are the holes. Here are the electrons. And the bands, parabolic bands, because I'm starting from the electron kind of things, roughly, just to get some dependence. And one has positive curvature, one has negative curvature. So up to here, it's just coming from the curvatures, no? But then, when you evaluate the effective mass, second derivative is the curvature. You will get one to have positive mass and one to have negative mass. So the holes will have negative mass. Does it make sense? I mean, just think. Let me see what else we can write. The momentum is equal to this. And then I can express the velocity as is equal, let's say, from here. So now if you have electrons, oops, the writing, electrons, I will have the velocity equal minus E tau over m, and the field for the holes What I want to emphasize that the velocity, the effective mass can be positive and negative, can be from 0 to infinity, and well, it will depend on the curvature. You can have bands like this, you can have bands like this. So you can try to analyze. The best way to study is to go through many cases, limiting cases of bands with very strong dispersion and very weak dispersion, and just see it for yourself. We will do it in class, but it's good that you go through it and understand. If you have a plane wave, if you have a localized band, if you have exactly at the edges, the velocity is 0, what happens? Just think of it for yourself, what it means. There is always a question in the exam on the effective mass. One question, always. Something. It's not difficult concept, it just requires a bit of thinking to go through it. Any questions? Let me see first if I finished. Okay. No, I wanted to mention here more that so this is the velocity, can be expressed like this. The current is velocity proportional to velocity and charge, all K and N and all these things. And in the very first time I mentioned the transport, I mentioned the Drude's conductivity, and that was here. It is the sigma times electric field. So this is the same current in a different way described. And Drude, this is what we are getting. But the real conductivity, not Drude's, but the real one is tau, the density of electrons or holes divided by the effective mass of holes or electrons. So you see, in this very simple approach, what we just used the free electron case, we derived the equation of the force, like hand waving, really. It cannot be any more hand waving, intuitive. We actually get a very, very correct expression on the conductivity, just not taking into account the density. The right terms. Do you have any questions on that? I'll give you problems which actually help you illustrate these things. Two problems. The first one is, it's very easy. I think at one point you have to understand this infinite mass. Otherwise it's a bit even boring, I mean, the first problem, but okay, one you should solve like that. Second one is a bit, it's easy up to a point, then discuss the usefulness of this concept. Can be tricky, you think of it. If you can distribute. I'm coming tomorrow. We'll continue with the applications of band theory and optical properties. I think on Thursday should be Nadia. And then again on Monday it's me. So I would say probably on Monday we can solve these if you want. The lecture is finished. Should I stop it?